Hello, and welcome back to Thinking in 6502, a series in which I share my learning journey with you as I explore the fascinating world of 6502 assembly programming, seen through the lens of higher-level programming languages such as BBC Basic. In this episode, we're going to be looking at creating custom characters, as well as demonstrating just how much faster your programs can run when they're written using assembly code. Now, as a quick aside, you're not going to see me do quite as much manual typing in this video, as the programs from here on in are going to get quite a bit longer and involve a fair number of, well, numbers. And my ability to type with precision, especially numbers, is not great. So instead, I'm going to be piping over the code via my PicoNet adapter. This is an ingenious little gizmo that lets me talk to my Electron from my laptop via Ethernet. This means I can get my programs all lined up on my PC and then just use a notify command to push them over to the Electron. It also works with the BBC Micro. It's a bit like having copy and paste available on an 8-bit machine, and it's pretty handy for these purposes. If you're interested in the PicoNet adapter, which supports many other helpful file transfer commands, do get in touch with Ken Lowe over on Stardot, as he is very much the brains behind this excellent device. Okay, so back to the central topic. In the last video, we encountered the VDU command in BBC Basic, which we used to print a single character to the screen instead of invoking the print command. For example, if we simply enter VDU67, we get a capital letter C. We can actually pass VDU multiple comma-separated values, and it will print all of them in a line. For example, VDU67, 79, 76, 73, 78 will print colon, since each of the values we pass correspond to each of the capital letters C, O, L, I, and N in the ASCII character set. VDU can do more than just print predefined characters, however. If we call it using the control character 23, we can pass our own custom characters, either as new characters or as redefinitions of existing ASCII characters. The character being defined, along with the values needed to supply that definition, are all passed to VDU in a single comma-separated list. If you're following along on a BBC Micro, by the way, do be aware that the effects of VDU with control character 23 will only appear in modes other than mode 7, which is of course the default mode on a BBC Micro. Not a problem on an Acorn Electron, of course, because sadly it has no mode 7. We're going to assume mode 6 from here on. So for example, if I wanted to create my own simple triangle glyph, I could customize character 240 as follows. VDU 23, 240, followed by this string of numbers. Now, whenever I print character 240, I will get this triangle. For example, print character string 240. I could even redefine an existing character and replace it with this triangle glyph. All I'd need to do is replace 240 with 65, which, as you'll recall from the last video, is the numeric byte value of the capital letter A. So I've got exactly the same VDU command now, except for the fact that my second number is 65 instead of 240. Now, whenever I type or print a capital letter A, I get the triangle glyph instead. What was once capital letter A will remain as the triangle glyph until or unless I hit break on my Electron, at which point it will reset back to an ASCII A once more. Using combinations of these custom character definitions, you can create your own fonts and graphics with relative ease. All you need to understand is what that string of 8 numbers means after the number designating the character that you want to redefine. It turns out they are simple byte values that come from adding up the numbers for each row of our 8x8 grid in base 2. You can think of your grid as follows. If you want to fill in blocks on that grid on a given row, you just need to add up the numbers. For a block on the far right, it's just a value of 1, whereas for a block on the far left, it's a value of 128. A value of 3, that is 2 plus 1, would fill in the first 2 blocks on the right, while a value of 192, which is to say 128 plus 64, will give me the first 2 blocks on the left. Now if I want all the blocks filled in for a given row, then I add up 128, 64, 32, 16, 8, 4, 2 and 1, giving me a total of 255. Might sound a bit more complicated than it is in practice, and to be honest, once you get the hang of it, it is really very easy to do. A lot of BBC Basic programmers have used this knowledge in the past to write their own simple character generator program that simply outputs the specific VDU command that you need, depending on what custom pattern you want to create. What is more, you can start to have even more fun by combining multiple custom character definitions together to form larger, more intricate graphics. For example, I could define 4 specific triangle glyphs. Then, having done that, I could combine them together in a 2x2 arrangement to create a diamond shape. So, now that we've established a reasonable way of creating custom characters in BBC Basic, how would we go about it in 6502 assembly? Let's first tackle the VDU command itself, as this is really at the heart of what we're doing in Basic. Although we've generated quite different results with the VDU command this time around, compared with the single character printing that we did in the previous video, it's important to stress that we're still doing fundamentally the same thing, passing bytes to VDU, which then translates them to what we see on the screen. Now, whether we use predefined characters or our own custom characters, ultimately it's still just patterns of pixels on the screen. The only difference being whether we use pre-existing patterns, which is to say the ASCII characters, in which case a single byte is sufficient, or else design those patterns ourselves, in which case we need to supply more bytes to get what we want. When thinking in 6502, we should ask what exactly are these bytes for. Let's break it down. When defining a custom character, we give VDU 10 arguments, the first being the control character 23, and the second being the numeric identifier of the character that we want to redefine. Remember that characters 0 through 127 are reserved by the operating system for letters, numbers, and punctuation marks, along with certain control characters, which of course includes 23. But this still gives us another 128 characters for our own potential use. Now, having told VDU which character we want to redefine, each of the subsequent 8 numbers we pass to it represent the 8 rows needed to construct a single character. These 8 numbers in binary representation are used to construct something called a bitmap, quite literally a map of bits, where 1 fills in a pixel and 0 does not. Each byte is a row in the 8x8 grid, with the individual 1s and 0s that make up the byte representing filled or empty pixels, respectively. To bring this to life a little bit more, imagine that we have the following 8 numbers: 28, 28, 8, 127, 8 again, 20, 34, and 65. Now I'm going to borrow Jonathan Harston's rather handy function b0 function, as it makes it nice and easy to convert decimal numbers to binary, which is not something that you can do natively in BBC Basic. Don't worry too much about what this program is doing, we're more interested in what the result is. Now that result looks like a bunch of 1s and 0s, but what I'm doing here is printing out the binary representation each time for each of those numbers. But what happens when we adjust the program ever so slightly? So I'm now going to switch the foreground color to black whenever we encounter a 0, and switch it to red whenever we encounter a 1, which will have the effect of the 0s not looking like they're printing, because of course black is also the background color. So if we run this adjusted program now, lo and behold, it's the famous stickman from the BBC Micro user guide. And this perfectly illustrates how bitmaps work. 1s become lit pixels while 0s remain unlit. Now, VDU with control character 23 in BBC Basic is just a convenient way of setting each of the 8 bytes that make up our bitmap in a single command. We could still create bitmaps without it though, using a method that much more closely resembles how we might do it in 6502 assembly. What we need is a place in memory to store our bitmap pattern, and then a way of passing that in byte by byte to a subroutine that can process it. VDU is, as you will remember, just a way to call our old friend OSWRCH, And just as passing a single byte to OSWRCH, provided it's a printable character, will result in writing that character to the screen, so if we pass a value of 23 to OSWRCH, it will then expect us to provide the remaining values that it needs to complete the call for defining a custom character. We can call OSWRCH in BASIC by using the call command followed by its memory address, just as we did in 6502 assembly code in the previous video with the JSR, or jump to subroutine opcode. And just like in 6502 world, where we had to place the value we wanted to print into the accumulator directly prior to our call to OSWRCH, we can do the same thing in BASIC, but just using the a% resident integer variable. Our basic program would then just need to follow a sequence of setting a% to a value, starting from 23, calling OSWRCH with each new a% value until we reach the final row of our bitmap. Now, while this is a very badly written basic program, it serves to make the point about how OSWRCH works when we start with a value of 23. A slightly better bit of basic might employ an array of values seeded from a data statement that we can then loop through. That data statement at the bottom, you can see, has 128, 28, 28, 8, 127, 8, 20, 34 and 65, which are each of the values that we need following the value of 23, which we are setting at line 30 in the program. And together, that would give us the equivalent of the VDU command that we were using before. What is more, this program is a better representation of how we would construct a similar program in 6502 assembly. The data statement here would be replaced with a starting memory address containing the bytes that we need. We already know from the last video how to build simple loops in 6502, so processing a series of bytes from a starting address using an index register will be very easy for us. Let's start by building a lookup table, as it's a fairly common requirement in 6502 programming. Now, a lookup table is really nothing more than a collection of bytes accessible via a label. In fact, it's often helpful to demarcate the lookup table with both a start and an end label, since this removes any interdependency when these lookup tables are stacked one on top of the other in the code. We'll start small and just define a lookup for our stickman. We can run this program just to see the machine code output, though at this point we've done nothing more than define some byte values and associate them to a label, so the program isn't going to do anything. But it illustrates the point. Each of the bytes that we need to define our stickman are now in a sequential place within memory, and you can see this much more clearly in the machine code output itself. To actually see the stickman, though, we're going to need to build our loop. Now we have a working version of our basic program, but rewritten in 6502 assembly. It calls OSWRCH with a value of 23, tells it that we want to redefine character 128, and then takes the bitmap rows from our lookup table, runs a loop to hand each one over to OSWRCH, and finishes by telling OSWRCH to then print character 128. Well, it's good as far as it goes, but to be honest, we haven't really done a great deal more assembly-wise than what we accomplished in the last video, even if the results might look a bit different. True to the spirit of the name of this series, we need to be thinking in 6502, much more so than our current program is actually doing. As humans, we're prone to thinking forwards sequentially, but in assembly programming we can work backwards just as easily. And more to the point, it is often to our advantage if we do, because we can save bytes and CPU cycles, making our code leaner and faster. Consider that CPX or compareX instruction at line 890. The additional 2 bytes and CPU cycles it's using could actually be stripped out, and we can still achieve the same result. To do this, we'll adjust the program slightly. Instead of initializing the X index register to 0, we'll initialize it to 7. Then we'll change line 880 to DEX or Decrement X instead of INX or Increment X. We don't want the CPX instruction at line 890, so we'll ditch that, and we're going to replace the BNE or branch not equal in line 900 with a different branch instruction, namely BPL. This stands for branch on plus. It will now branch all the while the X index register remains a positive value. Do note that although we're using it with X here, BPL can equally be used with the Y index register as well as the accumulator. It checks something called the N flag, which is a single bit value managed by the 6502, which gets set to 1, result is negative, or 0, result is positive, directly after any arithmetic operation in the accumulator or after any of the INY, INX, DEY, and, as here, DEX instructions. So what we're saying here is, on each iteration of the loop, subtract 1 from the X index register, and then check if the value of X is still positive. If it is, branch back to the stickman label, just as we were doing with our original BNE branch. The effect is that we load the last byte of our custom character definition into the accumulator, since we're offsetting by a value of 7 on the first iteration of the loop instead of 0. Then decrement and check if the result is still positive. Of course it will be, it'll now be a value of 6, so around we go again, this time offsetting by 6. On the final iteration of the loop, we will offset by 0, load that value into the accumulator, and decrement x, at which point it becomes -1, and so our exit condition via BPL is met. Of course, it does also mean that our stickman is now upside down. To rectify that, we need to rethink our lookup table as well. The bytes for our stickman's definition need to be reversed in order to support our new code. And now our stickman is back up the right way again. This goes to show that thinking in 6502 isn't just about how you write the code, it's also about how you structure your data. If a decremental loop is a faster or more efficient way to seed data in memory, then of course the bytes themselves need to likewise be ordered in reverse. There is actually more we can do here to properly demonstrate the power of 6502 assembly programming. After all, if all I did in this series was show you how to rewrite BASIC in 6502, wouldn't really be making much of a case for 6502. I mean, BASIC is quite a lot easier to program in. The primary reason, beyond of course the mental challenge and prowess that assembly programming offers, is speed. It's not the only reason, and we will look at some of those as well later in the series, but speed is why 8-bit games developers especially choose to code in 6502, and we can easily prove this point even with the small amount of material we've covered so far. Consider this simple BASIC program, once again featuring our favourite stickman. Now in mode 6 we have 40 characters per line and 25 lines in total, so I'm looping 25 times in the outer loop for each line, and then 40 times per line for each printed stickman on that line. By resetting the time variable to 0 at the start and then printing it again at the end, we get a rough idea of how long the code took to execute. It completes in roughly 1.4 seconds, which is not bad and certainly faster than I could draw 1,000 stickmen, but a machine running on a 6502 microprocessor could definitely do better. Let's go back to our assembly program from before, and instead of just printing a single character at the end, we'll fill the screen, just as we've done here in BASIC. We can similarly write a nested loop, with the X index register processing each column of the screen, and the Y index register processing each row. It's a loop within a loop. But since we don't care which direction we iterate in, we can just as readily count down as count up. The benefit is we don't need to compare X or Y to a specific value. We can just use the BPL opcode again to send the loop back around. When X or Y reach -1, the N flag gets set to 1 and the loop condition exits. Since we're doing a side-by-side comparison, I'm going to switch off the machine code listing and error checking by setting opt to 0 instead of 3. What's more, I'm not going to include the time taken to assemble the code in our timing benchmark, so we won't set time to 0 until after the code has been assembled, but before it's called, of course. This isn't cheating, I'm not trying to make the 6502 look even better than BASIC. The point is that when you write significant amounts of program code in 6502 assembly code, it is actually the assembled bytecode that the computer is running. The act of assembling that code is not technically part of the program itself. And there you have it, roughly 0.4 seconds, which is 70% faster than the same operation in BASIC. And that's with my assembly programming. There are doubtless much faster routines than this one that could achieve the same goal in even less time. Which is another benefit of assembly programming. Freedom. I'll never have a word said against BBC BASIC, it is after all the finest of all the BASICs ever produced. But the truth is, once you boil BASIC code down to its essentials, you will eventually hit a speed barrier that can't be crossed. It's an interpreted language at the end of the day. In assembly world, by contrast, there are all sorts of tricks that you can use to speed things up and squeeze ever greater performance out of the mighty 6502. It just requires adjusting how you go about solving the problem at hand, or thinking in 6502 as I like to say. Well, we've covered quite a bit of ground in this video, and it has set us up very nicely for the next episode, where I'm going to show you something called bit shifting, which is a technique used to manipulate bytes and bitmaps. I hope you found this video useful and that you'll continue following the series. It's been a real pleasure reading everyone's comments since the series began, and I am indebted once again to Chris Bradburn for all of his help. Behind the scenes, Chris and I exchange a lot of messages, mine filled with questions and mistakes, and his with answers and clarifications, and nearly all of it ends up in these videos one way or another. As I said at the outset, this series is very much a learn-as-I-go affair, and so I'm hugely grateful to Chris for all of his support. Do also watch out for the next 0-page episode, by the way, a companion video series in which I dive a little bit deeper into some of these topics for those of you who do want to go further. But until the next time, goodbye.